Hi, I'm Tzu-ying from the Department of Atmospheric Sciences, National Taiwan University. Here we will present the changes of canopy water amount in montane cloud forest under climate change. Montane cloud forest is recognized as a forest ecosystem in mountainous regions, with frequent cloud and fog occurrence. It has unique hydroclimatology characteristics and high biodiversity. This is a map of Taiwan, with green shading showing the distribution of montane cloud forests based on Schultz et al. 2017 study. Chilan is a cloud forest located in northeastern Taiwan, in a mountainous region at 1,650 meters above mean sea level. It is frequently immersed in cloud and fog, especially in the afternoon. A recent study showed that the canopy water amount in cloud forests is a critical element in fog formation, driving significant canopy evaporation when the sun rises, leading to a peak of land heat flux before noon and lower daytime temperature. However, climate change such as global warming is observed and modeled, which may change the amount of canopy water and thus fog formation. Therefore, in the study, we want to understand how the canopy water amount will change under future temperature and the mechanisms that drive this change. To understand the mechanisms that might lead to a difference in cloud forest and non-cloud forest sites, we also analyze a dataset from a non-cloud forest site, Lianhua in central Taiwan, whose atmospheric condition is quite different from Qilan. We use in-situ observations such as temperature, precipitation, radiation as the atmospheric forcings to drive NCAR CESM Community Lab Model version 4 and simulate canopy water and surface fluxes in Qilan and Lianhua. As for the climate change forcings, we use the temperature difference between the present and the end of century scenarios, downscaled using WOLF from the high-RAM climate model under RCP 8.5 scenario, and added the difference to the observational data to drive CLM4. Simulations with half and double temperature difference are also conducted to explore the variation under different warming scenarios. We expect that the canopy water in the two sites may decrease under warmer temperature due to decreased relative humidity and less dew condensation on the canopy at night. However, model simulations show the opposite response of canopy water to warming in two sites. This is the diurnal canopy water anomaly compared to the present-day simulations in Qilan in blue and in Lianhua in red. In Qilan, canopy water amount increases with the strength of warming, while in Lianhua, canopy water gradually decreases as expected. We analyze humidity changes and the anomaly of condensation, evaporation, and transpiration in each simulation, shown in this figure. In both Qilan and Lianhua, saturated specific humidity increases due to the higher temperature. However, the greatly increasing vapor from evapotranspiration in Qilan exceeds the increasing saturated specific humidity, therefore making more condensation at night in Qilan. While in Lianhua, although transpiration increases under higher temperature, the amount cannot reach the increase of saturated water vapor, leading to less condensation on the leaves, in turn less canopy water and less evaporation. We conclude the mechanisms that lead to the dipole response of canopy water amount under warming. When the temperature rises, saturated specific humidity increases according to the Clausius-Clapeyron equation, and Lianhua has a larger increase due to its higher mean state temperature. Evapotranspiration also increases under warming, but Qilan has a larger increase due to its moister mean state. The combining effect makes the increase of vapor exceeds the increased saturated vapor amount, favoring nighttime condensation. Therefore, more canopy water and canopy evaporation form a positive loop of the interactions. However, in Lianhua, the increased vapor cannot compensate for the change of saturated vapor, leading to a decrease in condensation, thus decreased canopy water and less evaporation in the next day morning, starting a loop of reducing water influxes. In this mechanism, the increase of specific humidity exceeding the increase of saturated amount is the key that leads to the difference response in two sites. In this presentation, we showed the increasing response of canopy water in Qilan under warming due to the increase of evapotranspiration, which may increase land heat and decrease sensible heat flux, leading to slower increasing daytime temperature and more favorable environment for fog formation. Yield data such as SIF, which provides primary production information, can be linked to ecosystem transpiration, can be used to validate the evapotranspiration from the community lab model. In this report, We haven't considered the effects of precipitation and other conditions such as land type, which is worth further researching. Finally, thanks for listening and feel free to ask any questions.